In this video, now that we have a basic understanding of one of the fundamental aspects of the car, which is running the motor, we're going to take a deep dive now into the rules and requirements provided by FSAE. We'll go through each step through all the relevant rules in the next couple of episodes together, and along the way justify and discuss our design decisions so we can then go into more details about our design for 2023's car. Once we go through all the rules and requirements, we can then kind of simply fill in the blanks of all the components that we chose for a specific application and how we met. So, our goals for today are going to make our previous circuit that we went over in episode 1 for running the car rules compliant, and introducing one of the most fundamental aspects of the car's functionality, the shutdown circuit. A quick refresher from the last video. Here is a diagram that we came up with for running our motor setup. Our decisions were influenced by what we needed to get a basic setup functioning, taking a bare minimum approach for the connections and signals we needed to actually feed to the motor controller to get it spinning. This is obviously though not rules compliant, so let's go through and start looking at some of the rules that we're going to need. Recall that we went through the vehicle's state machine, first starting on state 0. If you recall that there are 2 start sequences for our specific motor controller, and depending on which one you choose, you'll have to go through that certain start sequence to state 0. But once you're in state 0, it's going to immediately then go to the state 1, the pre-charge sequence initial state, which will turn on pre-charge relay pin, which ideally will go and power a relay, turning on a path that has a resistor in the way so it can, instead of activating all that power all at once to the motor controller, it can do it more gradually as you'll have a current limiting resistor. That kind of goes into step 2, waiting for the capacitors to finish charging, hence the resistor. And then step 3, the pre-charge finish state, where we'll do final checks. Obviously, we're then going into the next state where we can then actually, depending if we choose forward or reverse on that pin we talked about last time, you can then go into state 5 where the motor is energized and ready to start going. Before we get started, note that I won't be going in strict numerical order for the rules and requirements. I'm going based off what flows best for thinking about the design of the vehicle. To start, we'll talk about the accumulator isolation relays. These relays are going to be the main relays that engage high voltage to the car. So you can imagine that to be fairly sizable, as they must handle kilowatts of power when the motor is running. Here's a quick picture of the type that we use. You can see at the top the 2 screw terminals there. Those are the 2 main contacts for the relay. Then additionally, you see a red and a black wire. Those are the wires for the coil side of the relay that you'll put your 12 volts through to then close the contact. So, okay, we're going to need 2 AIRs and 1 fuse. So now the question is, where do we place the AIRs in the path of the high voltage? Because now we're going to have 2 instead of 1 like we had beforehand. So if we go down to the next rule, the accumulator isolation relays must be a normally open type. Okay, most relays are already like that, so we don't need to really worry about that. Both poles are open both poles of the accumulator. So what that is going to mean is that one relay is going to be gauging the high side of the voltage, and the other one is going to be gauging the low side of the voltage. If you look in the rules section for the electric vehicles, they actually have a diagram showing a basic setup of where these AIRs should go in the path of your high voltage. If you look in the box that has the dotted lines around it, you'll see there are 2 relays there called AIRs. One is on the very low side of the high voltage, and the other is on the very high side of the voltage. So let's go ahead and implement this configuration with a fuse and 2 AIRs into our setup. To start, I just went ahead and redrew our previous setup just so I can accommodate for some space for moving in some of those components now. So let's go ahead and make that change. So now we have a fuse going from the high voltage to the main AIR, goes through the motor controller, and then on the path to then the AIR on the negative side. But now there is a little bit of a question in regards to how do we power on the negative or the AIR on the negative side of the high voltage. Because beforehand, only having two relays, all we needed to do is engage the high side to either initiate the pre-charge, and then after the pre-charge, we can initiate that main AIR. But now it's like, what signal do we use for the negative side? Because the pre-charge and the main relay enable are going to need access to turn on this other relay. And we can't exactly hook them both up to the same time because say when the pre-charge is sending out 12 volts to that AIR, the main relay enable will also be connected to it and be powering that as well. And ideally, we don't want that because current's going to be running through both of those circuits at the same time now, and we could potentially damage the motor controller because it won't be going for the pre-charge as the motor controller can now just get instant access to the high voltage instead of being current limited with the resistor path. So the issue is now, how can we go about resolving having these two signals have the ability now to activate this third relay independently of one another and such. And this is where we're going to get into implementing some relay logic. So now, if you look at this diagram, we have something called RCB, or the relay control board. The main relay enable and pre-charge enable are now going to be input signals to this board, and the output signals are going to be going to the AIR, the pre-charge, or the AIR on the positive side, the pre-charge, and the AIR on the negative side. And so whenever now, say we do the pre-charge enable, it will first turn on the pre-charge relay and the AIR on the negative side. And then once the pre-charge turns off, when the main relay enable turns on, it'll activate the AIR, the main AIR on the positive side, and the AIR on the negative side. So that's how we can go around getting about this issue with having the two signals activating these three relays. Now, for the details of how the RCB actually works, we'll cover later in the series and such. But there's also still one kind of last component that we haven't talked about yet, and it's actually that little red line that you see going to the RCB, which is another signal called the shutdown circuit. And so I'd like to kind of explain the shutdown circuit through actually explaining the HVD, as these two are actually correlated to one another, as how to the shutdown circuit flows through the car. So let's go through that first and clear up the another main goal of this video, which is how the shutdown circuit works. The HVD, or high voltage disconnect, is the next main thing we'll cover in order to meet rules requirements. By definition, FSAE defines its functionality as a quick disconnect on one or both poles of the accumulator. To put this in more layman's terms, instead of always having the high voltage lines connected to the motor controller, we can simply separate the two with a connector, so we can add another factor of safety to our system, as beforehand we were only limited by our AIRs for engaging the high voltage. Some of these requirements are more mechanically related, such as the accessibility and visibility of the HVD on the vehicle. So this is a conversation we'll have more when we talk about the mechanical design further along the line. So let's keep our focus purely on the electrical side for now. So for us, that's going to be the first part of EV 6.5.1, which is a directly accessible element fuse or connector. In this case, the connector is going to be the most convenient, as there are a lot of pretty modular connectors that already exist out there made for high voltage connections and such. So utilizing those is going to be the easy path forward for us. Moving along, the next important rules is going to be EV 6.5.2, which is an interlock must open the shutdown circuit when the HVD is removed. So from these two requirements, two really main things jump to my mind immediately. One is, what is an interlock? And two, what is this shutdown circuit that we keep on talking about? Well, to start, an interlock is simply a feature that makes the state of two mechanisms or functions mutually dependent. In this case, that interlock function that's going to making our two independent functions mutually dependent is going to be for the shutdown circuit and the high voltage connection to the car. So when we connect our high voltage to the car, it's also going to be allowing the shutdown circuit to flow through it. Here's a quick photo of the type of connector that we use. This is a two-prong Amphenol connector, specifically designed for high voltage applications. So when you plug in the female side of this connector and fully engage it, it will allow one, obviously the high voltage to flow through it to the motor controller, and then additionally providing that other thing we talked about, the interlock function, which will allow the shutdown circuit to flow through it. So you'll see in the background that they're actually a red and a black wire. These are actually attached to an internal mechanism on this panel mount connector. So when you press in the female side of the connector to these two prongs and fully engage it, it will actually make a mechanical connection to those two wires, allowing a voltage to flow through them. Now, note this isn't the high voltage that's going to be flowing through it. This is going to be an external connection that we're going to make to the shutdown circuit. So let's go ahead and look at a diagram real quick of all of this kind of put together and such. So you see, I simply just drew a box now representing our accumulator and putting that panel mount Amphenol connector on here. So you see, if we trace out the path from the high voltage, we see that it first goes to that first prong of the connector. And then we'll see once we have, say for example, we plug in the motor controller, high voltage will flow through the motor controller, then to the other side of that connector, negative side, and then to the negative high voltage of the car. So once that connector is fully engaged, you'll see that we have that interlock system that we were talking about. So when that connector fully engages, it's going to be activating a mechanical mechanism. You can basically just think of it as a switch that will allow a continuous connection between those two wires now. And that's where our shutdown circuit is going to be flowing. But now the question is, what exactly is a shutdown circuit? So the main purpose of the shutdown circuit is going to be giving us the ability to shut down the car at several points along the physical layout of the car. So if we look here, just starting from the BSPD or the brake plausibility device, going down the line, we can see that there are several e-stops, such as a cockpit e-stop left and right. So these are going to be physical buttons on the car that will physically stop the car when we press in on that button. And what allows that to happen, if we trace out the rest of the shutdown circuit, we can see that the shutdown circuit actually goes to powering the relays or the AIRs in the accumulator. So we'll be able to turn off the relay power at several points of the car, which is why we call it the shutdown circuit. And so now routing that shutdown signal to the RCB, whenever, say, for example, we have the main relay enabled, that shutdown circuit is going to flow through the positive AIR and the negative AIR to physically power it. And then since we have the rest of the shutdown circuit that is going to be basically a disconnect point that we can press at any time, we can manually shut off those AIRs, disconnecting the high voltage. So really, the main takeaway from this is that the shutdown circuit has to be fully complete in order for the car to be able to run. Now, how the RCB is designed, it allows the shutdown signal to flow to those relays whenever we have those two connections from the motor controller activated. So say the pre-charge enable is high. It's going to allow the shutdown circuit to flow to the pre-charge relay and the negative AIR relay. And then once the pre-charge is done, that will shut off. And then enable the main relay enable, allowing the shutdown signal now to flow to the positive AIR and then to the negative AIR afterwards. For more of a technical description of the RCB, like I said earlier, we're going to be covering in a future video. So hold on for that. The next video we'll be going over the pre-charge and discharge circuits. This is going to be more going over the technical aspects for making it rules requirements, such as choosing values for that resistor for the pre-charge circuit and certain requirements that we're going to need to meet as well for charging up our motor controller in a certain amount of time and meeting other requirements like that. So see you in the next video.